Look around you for a moment. Somewhere nearby, a cup of coffee is cooling down. Maybe there is ice slowly melting into water. Heat is moving, always in one direction, always from hot to cold. You have seen this your entire life, so often that it feels like a law deeper than physics itself. But here is the strange part, nothing in the fundamental laws of motion actually forbids the opposite. There is no equation that says heat cannot suddenly flow backward, that a cold cup cannot warm itself, that scattered energy cannot gather itself together again, and yet it never happens, not once, not ever. This is the kind of mystery that hides in plain sight, so familiar that we stop questioning it. Why does nature choose this direction and not the other? Why is time itself tied to this simple, irreversible flow? In the 19th century, a physicist named Clausius looked at this ordinary phenomenon and realized it contained an extraordinary secret, one that would change how we understand time, probability, and the very structure of reality itself. It feels obvious, doesn't it? Of course, heat flows from hot to cold. Of course, a hot object cools down and a cold one warms up. It feels so natural that questioning it almost sounds foolish. But that sense of certainty is exactly where the illusion begins, because when you zoom in far enough down to the level of atoms and molecules, that obviousness completely disappears. At that scale, everything is just particles moving, colliding, bouncing off one another according to precise mathematical rules. And here is the unsettling part. Those rules do not care about direction. They do not distinguish between past and future. If you could watch a microscopic collision and then play it backward, the motion would still obey the exact same laws. Nothing would look wrong. Nothing would violate physics. The equations would be perfectly satisfied in both directions. Imagine a swarm of tiny particles in a box, constantly colliding and exchanging energy. Run the film forward. It looks normal. Reverse it. It still looks physically possible. There is no built-in arrow telling the system which way time is supposed to flow. And yet, in the world you experience, there is a clear direction. Heat spreads out, never gathers itself back together. This is where the tension begins to build, because if the fundamental laws are completely symmetric, then where does this one-way behavior come from? Nothing in Newton's laws says heat must flow from hot to cold, and yet the universe insists that it does. Now step even closer, beyond what your eyes can see, into the restless microscopic world where heat truly lives. What you call heat is not a substance, not a fluid, but motion. When something is hot, its particles are moving faster, vibrating more intensely, colliding with greater energy. When something is cold, those same particles move more slowly, drifting with less urgency. That is all temperature really is, a measure of motion. Imagine two groups of particles brought into contact. One group is fast, energetic, chaotic. The other is slow, calm, almost still. The moment they meet, collisions begin. Fast particles strike slow ones, transferring energy. Slow ones gain speed, fast ones lose it. The system starts to mix, to blur, to even out, and because these collisions happen constantly and randomly, energy spreads through the entire system. Eventually, everything reaches a kind of balance, a uniform state where no region is distinctly hotter or colder than another. You have seen this happen 1,000 times without thinking about it, but now pause and really picture it. Each collision is random. Each interaction is just one particle bumping into another with no grand plan, no guiding intention. There is no rule telling them to distribute energy evenly. There is no hidden force pushing them toward balance. It is just chaos, repeated over and over again. And yet somehow that chaos always leads to the same outcome. The energy spreads out, the differences disappear. The system smooths itself into uniformity. And here is the paradox that should bother you. If every motion is random, if every collision could just as easily go one way as the other, then why does it always move toward equilibrium? Why does randomness consistently produce order in one direction and never the reverse? Why don't we ever see the slow particles suddenly give their energy back, recreating the original imbalance? Why doesn't randomness sometimes reverse itself? Now comes the part that unsettles even physicists. The equations that govern motion, the ones describing every collision between particles, do not care about time moving forward. They work just as well if time is reversed. This is not a philosophical statement. It is a mathematical fact. Take any system of particles, let them collide, scatter, exchange energy, and then record the entire process. Now play that recording backward. Every particle still follows the same laws. Every collision still conserves energy and momentum. Nothing in the equations breaks. Nothing signals that something is wrong. To physics itself, forward and backward are indistinguishable. Try to picture this clearly. Imagine a box filled with gas. At first, all the particles are crowded into one corner. Then you remove a barrier and they spread out, filling the entire space. That is what you expect. Now imagine filming this process and reversing the video. Suddenly, particles from all over the box begin moving in perfect coordination, converging into a single corner again. It looks absurd, almost magical, but every individual motion still obeys the same physical rules. This is the paradox. If the laws of physics allow both directions equally, if nothing forbids this reverse behavior, then why does the universe never choose it? Why do we never witness energy spontaneously gathering itself, heat flowing backward, disorder organizing itself into perfect structure? For decades, this question haunted scientists. It was not a small detail or a technical glitch. It was a deep crack in our understanding of reality. Because if the fundamental laws are reversible, then something else must be responsible for the direction we experience. And whatever that something is, it defines the arrow of time itself. Rudolf Clausius approached this mystery from a completely different angle. He did not try to rewrite the laws of motion or invent new forces to explain why heat behaves the way it does. Instead, he asked a deeper question: what if the answer is not hidden in the rules themselves, but in the number of ways those rules can play out? This shift in thinking was subtle, but it changed everything. Clausius realized that when energy spreads out, there are vastly more ways for that to happen than for it to concentrate. Imagine your room right now. There are countless ways for it to be messy. Clothes on the chair, books scattered, objects out of place in endless combinations. But there are very few ways for it to be perfectly clean, where everything is arranged just right. Order is rare, disorder is overwhelmingly common. Now apply that idea to particles. When gas is confined to one corner of a box, there are only a limited number of ways for all those particles to stay packed together, but once they are free to move, the number of possible arrangements where they are spread out across the entire box becomes astronomically larger. Each particle can be almost anywhere, moving in almost any direction, creating an explosion of possible configurations. Clausius introduced a way to capture this idea with a single concept. He called it entropy. At its heart, entropy is a measure of how many different ways a system can be arranged while still looking the same at a large scale. A low entropy state is highly ordered with very few possible arrangements. A high entropy state is disordered with an enormous number of possibilities. And here is the key insight that resolves the paradox. Systems do not evolve toward equilibrium because they are forced to. They evolve toward equilibrium because it is overwhelmingly more likely. Heat flows from hot to cold, not because the reverse is impossible, but because there are far more ways for energy to be spread out than to be concentrated. The universe is not following a rule that demands disorder. It is simply moving toward what is statistically inevitable. And this is where the truth becomes almost unsettling. Heat flowing backward is not forbidden. There is no cosmic rule that prevents it, no hidden law that makes it impossible. In principle, every particle in a system could reverse its motion in just the right way, transferring energy back into a smaller region, recreating the original imbalance. The equations allow it, the physics permits it, but the probability is so unimaginably small that it might as well never occur. To understand this, think about the air around you right now. It is made of an enormous number of molecules, all moving randomly, colliding, spreading out evenly through the room. Now imagine every single one of those molecules suddenly gathering into one corner, not gradually, not with some guiding force, but purely by chance. It is not impossible. There is nothing in physics that forbids it, but the number of ways for the air to be evenly spread out is so vastly larger than the number of ways for it to be confined to one corner, that the odds of it happening spontaneously are essentially zero. The same logic applies to heat. For heat to flow backward, every collision would have to align perfectly. Every particle would need to move in just the right direction at just the right moment. It would require an absurd level of coordination emerging from pure randomness. When you try to calculate how unlikely this is, the numbers become so extreme that they lose all intuitive meaning. It is not just unlikely in the sense of rare. It is unlikely on a scale where even the entire lifetime of the universe is not enough time for it to reasonably occur. So when you say that heat never flows backward, what you are really saying is something deeper. It is not forbidden. It is just so unlikely that the universe will die before it happens. And this is where everything comes together in a way that feels almost unsettling. The direction of heat flow is not just about temperature. It is about time itself. Because what Clausius revealed is that the arrow of time, the sense that the past is different from the future, comes from entropy increasing. The past is always a state of lower entropy, more ordered, more structured, more constrained. The future is a state of higher entropy, more spread out, more disordered, more probable. When you watch a process unfold, what you are really seeing is entropy rising. That is why it feels natural, why it feels inevitable. Time flows in the direction of increasing disorder. And once you see this, you start to notice it everywhere. A glass shatters but never reassembles. Your body ages but never reverses itself. Memories form in one direction, from past to future, never the other way around. You remember yesterday, but you cannot remember tomorrow. All of this is tied to the same underlying principle. The increase of entropy is what gives time its direction, what separates what has happened from what has not yet occurred. It is not just a physical process. It is the foundation of your experience of reality itself.